Hello everyone and welcome to Kaylee Society's College of Education, Ankola. My name is Anusha Koti and I am B.Ed first year teacher student.
In your previous chapter, we learned about the heating effects of electric current. What could be the other effects of electric current? Do you know what is this? Yes, it is a magnet. Do you know what are the properties of magnet? A magnet is an object that attracts or repels other magnetic materials with its magnetic field. In today's unit, we will discuss about magnetic effects of electric current, magnetic fields, and such electromagnetic effects. We shall also study about electromagnetic and electric motor which involve magnetic effect of electric current. We know that electric current carrying wire behaves like a magnet. Let us begin with an experiment. Take a straight thick copper wire and place it between the points X and Y in an electric circuit as shown in the figure. The wire XY is kept perpendicular to the plane of paper. Horizontally, place a small compass near to the copper wire. See the position of the needle. Pass the current through the circuit by inserting the key into the plug. Observe the change in the position of the compass needle. We see that the needle is deflected. What does it mean? It means that the electric current through the copper wire has produced a magnetic effect. Next, we will see magnetic field and field lines. We are familiar with the fact that a compass needle gets deflected when brought near a bar magnet. A compass needle is in fact a small bar magnet. The ends of the compass needle point approximately towards north and south directions. The end pointing towards north is called North Pole and south is called South Pole. Fix a sheet of white paper on a drawing board using some adhesive material. Place a bar magnet in the center of it. Sprinkle some iron fillings uniformly around the bar magnet. Salt sprinkler may be used for this purpose. Now tap the board gently. What do you observe? Iron fillings near the bar magnet align themselves along the field lines. The region surrounding a magnet in which the force of magnet can be detected is said to have a magnetic field. The figure shows the field lines around the bar magnet. Next, we will see magnetic field due to a current carrying conductor. A straight electric circuit in which a straight copper wire is placed parallel to and over a compass needle. The deflection in the needle becomes opposite when the direction of the current is reversed. Next, we will see magnetic field due to a current through a straight conductor. What determines the pattern of the magnetic field generated by a current through a conductor? Does the pattern depend on the shape of the conductor? We shall investigate this with an activity. We shall first consider the patterns of the magnetic field around a straight conductor carrying current. From the figure, it can be noticed that the concentric circles representing the magnetic field around a current-carrying straight wire becomes larger and larger as we move away from it. A pattern of concentric circles indicating the field lines of a magnetic field around a straight conducting wire. The arrows to the circles show the direction of the field lines. A close-up of the pattern obtained. Next, we will see right hand thumb rule. A convenient way of finding the direction of magnetic field associated with the current carrying conductor is given in the figure. Imagine that you are holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of current. Then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field as shown in figure. This is known as the right hand thumb rule. We have so far observed the pattern of the magnetic field lines produced around a current carrying straight wire. Suppose this wire is bent in the form of a circular loop and a current is passed through it. How would the magnetic field lines look like? We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it. Similarly, at every point of a current carrying circular loop, the concentric circles representing the magnetic field around it would become larger and larger as we move away from the wire, as shown in the figure. By the time we reach at the center of the circular loop, the arcs of these big circles would appear as straight lines. Next, we will see magnetic field due to a current in a solenoid. A coil of many circular turns of insulated copper wire wrapped closely in a shape of a cylinder is called a solenoid. The field lines inside the solenoid are in the form of parallel straight lines. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside the coil. The magnet so formed is called as electromagnet. Next is force on a current carrying conductor in a magnetic field. We have learned that an electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on a magnet placed in the vicinity of the conductor. French scientist André Marin Ampère suggested that the magnet must also exert an equal and opposite force on the current carrying conductor. The force due to a magnetic field acting on a current carrying conductor can be demonstrated through the following activity. A current carrying rod AB experiences a force perpendicular to its length and the magnetic field. Suppose for the magnet is not shown here for simplicity. The direction of the force on the conductor depends upon the direction of current and the direction of the magnetic field. Next we will see Fleming's left hand rule. Fleming's left hand rule. According to this rule, stretch the thumb, forefinger and middle finger of your left hand such that they are mutually perpendicular. If the first finger points in the direction of magnetic field and the second finger in the direction of current, then the thumb will point in the direction of motion or the force acting on the conductor. Devices that use current carrying conductors and magnetic field include electric motor, electric generator, loudspeakers, microphones and measuring instruments. Next is electric motor. An electric motor is a rotating device that converts electrical energy into mechanical energy. A device that preserves the direction of flow of current through a circuit is called a commutator. In electric motors, the split ring acts as a commutator. Now, let us imagine a situation in which a conductor is moving inside a magnetic field or a magnetic field is changing around a fixed conductor. What will happen? This was first studied by English physicist Michael Faraday. Faraday made an important breakthrough by discovering how a moving magnet can be used to generate electric currents. A galvanometer is an instrument that can detect the presence of a current in a circuit. The pointer remains at 0, the center of the scale. For zero current flowing through it, it can deflect either in the left or to the right of the 0 mark depending on the direction of current. Fleming's right hand rule. Stretch the thumb, forefinger and middle finger of right hand so that they are perpendicular to each other as shown in figure. If the forefinger indicates the direction of the magnetic field and the thumb shows the direction of motion of the conductor, then the middle finger will show the direction of induced current. This simple rule is called Fleming's right hand rule as shown in the figure. Next we will see electric generator. Based on the phenomena of electromagnetic induction, the experiments studied above generate induced current, which is usually very small. This principle is also employed to produce large currents for use in homes and industry. In an electric generator, mechanical energy is used to rotate a conductor in a magnetic field to produce electricity. The difference between the direct and alternating current is that the direct current always flows in one direction, whereas the alternating current reverses its direction periodically. Most power stations constructed these days produce alternating current. In India, the alternating current changes direction after every second. That is, the frequency of alternating current is 50 Hz. Next, we will see Domestic electric current. Electric fuse is an important component of all domestic circuits. We have already studied the principle and working of a fuse in the previous chapter. A fuse in a circuit prevents damage to the appliances and the circuit due to overloading. Overloading can occur when the live wire and the neutral wire come into direct contact. In such a situation, the current in the circuit abruptly increases. This is called short circuiting. Overloading can also occur due to an accidental hike in the supply voltage. Sometimes overloading is caused by connecting too many appliances to a single socket. This completes the chapter Magnetic Effect of Electric Current. Thank you. Please like, comment and share.